three-dimensional space might not actually exist. This isn't some philosophical thought experiment. Back in the late 1990s, physicists built a mathematical model showing that all the laws of gravity inside a volume of space match perfectly with the laws of quantum theory on its flat, two-dimensional boundary. Two completely different theories, one and the same reality. If this model holds true, then the depth we experience, whether it's the space between your hand and a wall or from Earth to the sun, could just be a computational illusion. And here's the unsettling part. We don't have a single instrument capable of telling the difference between real volume and a flawless hologram. Take a simple sheet of paper. Run your finger across it. The rough cellulose feels warm to the touch. The sheet has length, width, and a barely noticeable thickness. Imagine this sheet as the entire universe. Its flat surface holds the equations of quantum field theory, a theory with no gravity at all. Particles, fields, interactions, all strictly two-dimensional. But when these flat structures begin to interact in a certain way, a new dimension literally grows above the sheet of paper, a third dimension. In it, strings appear, gravitational attraction emerges, and what we know as space comes to life. This isn't just a thought experiment designed to sound poetic. It's a mathematical model known as anti-de Sitter space, a solution to Einstein's equations featuring a negative cosmological constant. In simpler terms, it's a stripped-down version of the universe where space curves inward, like the bottom of a deep bowl, and it has a clear, well-defined boundary. And here's what they discovered. The theory of gravity inside this space, the superstring theory with all its dimensions and vibrating strands, turns out to be mathematically identical to the ordinary quantum particle theory on its flat boundary. Two languages, one meaning. Write down the formula for gravitational interaction between two objects within the volume, and it matches exactly the formula for quantum interaction on the surface. The entropy of a black hole inside this space equals the thermodynamic entropy of radiation on its boundary. Picture two columns. On the left, volume, gravity, strings. On the right, surface, quanta, fields. Between them stands an equal sign. Remember this structure. It will come back. What does this space look like? Think of M.C. Escher's prints, the ones where fish or lizards shrink smaller and smaller as they approach the edge of a circle until they compress into an infinitely thin line along the frame. In anti-de Sitter space, something similar happens. As objects move away from the center, time slows down more and more, just like near the event horizon of a black hole. Toss a ball in any direction. It slows, stops, and then comes right back. This space is closed. It has an edge, and according to calculations, all the information about what's happening inside is encoded right on that edge. But here's the strange part. We feel depth. We live inside it, and we have every reason to trust that feeling. Einstein's theory of relativity fused space and time into a single continuum and set a firm rule. Nothing in the universe can move faster than light. This theory isn't just elegant, it works every second. Navigation satellites orbiting Earth constantly adjust their clocks because time actually runs a tiny bit faster up there than on the planet's surface. The difference is minuscule, just nanoseconds per day. But on the sun's surface, the effect of time slowing down is 1,000,000 times stronger. And on the surface of a neutron star, a super dense remnant of a dead star, where a teaspoon of matter weighs as much as a mountain range, time flows 30% slower than it does far away. Each second there lasts only 700 milliseconds. We can measure it, and we have measured it. Gravity slows down time. Mass warps space. Planets follow geodesics. Every detail has been confirmed. Every prediction tested. We believe in a three-dimensional world not out of naivety. We believe because it stands up to every test. And yet, if the laws inside a volume and the laws on its boundary are one and the same, then which comes first? What if the gravity we know isn't a fundamental rule, but a side effect? Not a law, but a shadow of a law. To get closer to the answer, we have to leave cosmology behind and descend into a realm without stars or distances, just closed surfaces and the question of how much information a boundary can hold. Let's start with something simple. A star is defined by dozens of parameters: its chemical makeup, age, brightness, magnetic field, rotation speed, and stage of evolution. A planet is even more complex. Its atmosphere, geology, orbit, and axial tilt all come into play. Even a simple rock on the road demands molecular analysis to fully understand it. But if that same rock, star, or even a whole galaxy collapses into a black hole, suddenly all that complexity vanishes. No matter its composition or history, any black hole can be completely described with just two numbers: its mass and its spin. Two numbers. Physicists call this the no-hair theorem. In other words, black holes are the simplest large-scale objects in the universe. And here's where the problem arises. Not a philosophical one, a thermodynamic one. Entropy measures how chaotic a system is. You can think of it as the number of ways you can rearrange the internal parts of an object without changing how it looks from the outside. A glass of water has enormous entropy. Its molecules can shuffle in trillions upon trillions of ways, yet the water stays the same. A crystal has less entropy, and an ideally ordered lattice at absolute zero has almost none at all. The second law of thermodynamics states that the entropy of a closed system can never decrease. Chaos doesn't shrink on its own, ever. But when a star collapses into a black hole, all its internal degrees of freedom, trillions of parameters, compress down to just two numbers. So where did all that entropy go? It can't just vanish. That would break the second law. Physicist Jacob Bekenstein found the answer in the early 1970s, and the answer turned out to be strange. Bekenstein calculated that the entropy of a system collapsing into a black hole is always less than 1/4 of the area of its event horizon. Not the volume, the surface area. The entropy of a black hole is encoded on its two-dimensional boundary, like writing on the skin of an orange, not its juicy interior. This wasn't a hypothesis. It was a mathematical result, a formula. And it revealed something unexpected. There is a theoretical limit to the amount of information any enclosed space can hold. The perfect object carrying the maximum information per unit area turned out to be exactly a black hole. Now here's the crucial step. Imagine a region of space packed with so much information that its density exceeds the Bekenstein bound. What happens next? The matter collapses. Gravity won't allow that density to exist. The region shrinks down into a black hole. And as we just learned, a black hole stores all its information on its surface. It creates a catch. If you try to cram more information into a volume than the boundary allows, the volume destroys itself. It turns into an object whose capacity depends only on its surface area. Here's an analogy that reveals just how absurd this is. Imagine a room, walls, floor, and ceiling. It's packed with books, shelves stretching from floor to ceiling, wall to wall. Common sense tells us the bigger the room, the more text it can hold. Double the volume, double the library. But the Bekenstein limit says something else. The maximum amount of information you can physically store in this room doesn't depend on its cubic volume. It depends on the surface area of the walls. The wallpaper, if you will. Double the room's volume, but the wall area grows by less than double. The information capacity rises by less than double too. This isn't a metaphor, it's a mathematical fact. This idea leads to a principle that upends our intuition about space. The holographic principle states that a complete description of any physical system inside a volume can be entirely encoded on its two-dimensional boundary. The information contained within that volume never exceeds the information on its surface. Everything happening in three-dimensional space, every particle, every interaction, every motion is, in principle, recorded on the two-dimensional surface surrounding it, without any loss. The third dimension, the depth we take for granted, is actually redundant, not wrong, and not an everyday illusion, but mathematically unnecessary. all the information already exists on the boundary. Thermodynamics gave us a precise formula, a clean, elegant boundary. But a formula is one thing. The real physical world, where virtual particles pop in and out of existence at the event horizon, is something else entirely. And when quantum mechanics met this boundary, the outcome wasn't elegant. It was catastrophic. Disaster begins with emptiness. More precisely, with the fact that emptiness doesn't actually exist. Werner Heisenberg's uncertainty principle forbids us from knowing both the exact position and exact speed of a particle at the same time. This isn't a flaw in our instruments, it's a fundamental property of reality. And it has a consequence that makes the physical world utterly unrecognizable. The vacuum, the very thing we think of as absolute silence, is actually boiling, constantly, everywhere, right now. From nothing, pairs of virtual particles are born. A particle and its antiparticle flare into existence, live for a fraction of a moment, then annihilate back into nothing. This isn't just a metaphor, it's a measurable, experimentally confirmed process. Space shivers with tiny ripples on scales billions upon billions of times smaller than an atom. And this ripple, invisible, inaudible, existing at the edge of what we can measure, can destroy a black hole. When a pair of virtual particles suddenly appears right at the event horizon, something breaks apart. One particle falls in, the other escapes. The one that falls carries negative energy with it. The one that escapes takes positive energy away. To an outside observer, this looks like a faint thermal glow, as if the black hole is softly smoldering. Stephen Hawking calculated the temperature of this glow back in 1974. Here's what he found. The temperature is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it gets. And the hotter it gets, the faster it loses mass. The process speeds up. It accelerates. The final moments of evaporation burst out in a flash. Then, nothing. The black hole disappears. Where does all the information it has absorbed over billions of years vanish without a trace? Every atom, every photon, every path of every particle that ever crossed the horizon, it's all encoded in the entropy of the black hole. Hawking radiation is thermal, random. It carries no clue about what fell inside. It's like burning a library and trying to recover the texts by measuring the smoke's temperature. Quantum mechanics insists that information can never disappear. Never. It's one of its fundamental laws. But a black hole, as it evaporates, does exactly that. It destroys information. Two pillars of physics face each other, and one of them is lying. God does not play dice, Einstein once said. His theory is classical, deterministic. It defines exact trajectories, precise curves, definite answers. Quantum mechanics stands in stark contrast. It deals in probabilities. A particle isn't fixed at a single point. It's spread out across a cloud of possible states. Both theories have been tested to an accuracy of 10 decimal places. Both work. Yet they describe different realities that refuse to align at the event horizon. Physicists have managed to unite 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force, all folded into the standard model. Gravity remains outside, the only force that resists quantization. And here, an unexpected bridge emerges. String theory wasn't originally developed to explain gravity. It started out describing the strong force, that powerful glue holding quarks together inside protons. But when physicists began exploring how quarks and gluons behave at the edge of a special kind of space, the so-called anti-de Sitter space, they found something surprising. The interactions of these particles formed objects that looked like strings. These strings, stretched deep into the space, acted like a gravitational field. The thickness of a string depended on how far the equivalent particles were from the boundary. And one particular combination of gluons at this boundary turned out to be mathematically identical to a graviton, the quantum of gravity, a particle no one has ever seen, but that must exist if gravity follows quantum rules. So, the strong force on the surface and gravity in the volume might actually be the same phenomenon, spoken in two different languages. But possible doesn't mean proven. We still don't have a quantum theory of gravity. Humanity's two main theories, one about the very large, the other about the very small, clash head-on right where we need answers the most, at the edge of a black hole, in the first moments after the Big Bang, at points where space compresses to scales where quantum fluctuations and the curvature of space-time collide directly. This clash might seem like a modern scientific puzzle, but the idea that gravity could create insurmountable boundaries appeared long before the quantum era, back when light was still thought to be a stream of tiny particles. Paris, late 18th century. Pierre-Simon Laplace, a mathematician, astronomer, and one of France's most brilliant minds, sits at his desk wrestling with a problem that seems completely impractical. He's trying to figure out what would happen to a beam of light if it were emitted from the surface of an object so massive that even light couldn't escape. His reasoning is straightforward. To throw a stone upward and send it away from Earth forever, it needs to reach a speed of 11.2 kilometers per second. For the Sun, that speed jumps to 617.7 kilometers per second. The more massive the body, the faster you have to move to break free from its grip. By that time, Laplace already had two crucial facts at his disposal. The first was Newton's laws of motion, which described gravity as a force dependent on mass. The second was that light travels at a finite speed. This was established back in the 17th century by Danish astronomer Ole Romer, who observed Jupiter's moons and noticed their eclipses delayed when Earth moved away from Jupiter. Laplace combined these two facts. If light is a stream of tiny particles, corpuscles, as Newton taught, then gravity must affect it. That means you can calculate the mass of an object whose escape velocity exceeds the speed of light. He called such an object a dark body, corps obscurs. A body so massive that no particle of light can escape its surface, invisible by definition. Laplace didn't build telescopes or send out expeditions. He simply looked up at the night sky and asked, what if objects hide between the stars that we simply can't see? This was before relativity, before quantum mechanics, before anyone even thought of light as a wave. Yet the idea was already born. More than 120 years have passed. It is 1916. German physicist Karl Schwarzschild serves on the Eastern Front during the First World War. Between calculating artillery trajectories, he receives a fresh paper from Einstein on the general theory of relativity and sets out to find an exact solution to its equations. He solves it within weeks. Then, he sends the result to Einstein by regular mail from the front lines. 5 months later, Schwarzschild dies from illness. But his solution outlived him by over a century. It predicted something that even Einstein initially dismissed. Around a point-like massive object, there exists a region of space where time completely stops. Not just slows down, it stops altogether. This region would later be called the event horizon. Here's what this means. Every morning, you toss your keys onto the table. They fly, clatter, and fall. Time moves the same for you and for the keys. That's familiar physics. Now, imagine an event horizon. From a distance, if you watch an object falling toward this boundary, it'll start to slow down, not because of any braking force, but because time itself flows differently near that edge. The object dims, reddens, as if it's sinking into thickening glass. To an outside observer, it never actually crosses the horizon. It freezes there, slowly fading into darkness. But for the falling object itself, nothing unusual happens. It passes through the boundary without feeling any stop. Time flows smoothly for it. Two observers, one event, two completely different experiences of time. Laplace's intuition and Schwarzschild's mathematics described an object that seemed purely abstract. But the universe proved more generous than any formula. Black holes exist, and they form in at least two ways. A supermassive star, tens of times heavier than the Sun, burns through its fuel. Then, its core collapses inward within fractions of a second. This is gravitational collapse. The second path is even grander. Entire clouds of gas and dust at the centers of young galaxies compress, giving birth to monsters weighing millions or even billions of times the mass of the Sun. Now, here comes the strangest part. An object that traps light is surrounded by one of the brightest structures in the universe. Matter pulled in by the black hole doesn't fall inside instantly. Instead, it spins into an accretion disk, a swirling ring of gas and dust, hurtling at speeds close to the speed of light. The friction inside this ring is intense. Temperatures soar into the millions of degrees. This blazing disk emits radiation so powerful it can outshine an entire galaxy. In simple terms, the black hole itself remains invisible, but its cosmic feast shines brighter than a billion stars. Laplace predicted it 2 centuries before anyone could prove it. Schwarzschild formulated the math, but never lived to see it accepted. The event horizon turned out not to be a fantasy of a few isolated thinkers, but a fundamental feature of space, a boundary where the very rules of the universe shift. And if such a boundary naturally forms around every black hole, a quiet but persistent question remains. Could something like this exist not just around collapsing stars, but at the level of space itself? Maybe it does. And if that's true, then Newton takes the first hit. For over 300 years, the formula force equals mass times acceleration stood as a fundamental law of nature. Not a consequence of something deeper, not an approximation, the foundation itself. But when you take the holographic screen, the very boundary where information about the system is encoded, and apply thermodynamics to it, the whole picture flips. An entropic force, similar in nature to osmosis, pushes the system's boundary outward, driven to increase overall entropy. Through mathematical transformations involving the Unruh effect, a phenomenon where an accelerating observer detects temperature in empty space, this force leads precisely to the formula force equals mass times acceleration. Inertia isn't an inherent trait of matter. Inertia is a thermodynamic effect. Next, imagine a spherical holographic shell with information spread evenly across its surface. We express its temperature using the equivalence of mass and energy, the famous equation E equals mass times the speed of light squared. Running the calculations, we derive Newton's law of universal gravitation, not as an assumption, but as a consequence of statistical behavior at the boundary. This exact framework, boundary, information, temperature, force, that once explained black holes now recreates classical mechanics. The concept feels familiar, but the scale is entirely different. But if gravity is just a consequence of entropy, not a fundamental force on its own, then cosmology faces a problem it has struggled with for decades. The universe is expanding at an accelerating pace. To explain this acceleration, scientists introduced the concept of dark energy, a mysterious substance that fills space and pushes galaxies apart. The catch? When theorists tried to calculate the density of this energy using quantum field theory, their results missed the mark by an astonishing 120 orders of magnitude. 120 orders. To put that into perspective, imagine someone asks how much an apple weighs, and your calculation estimates the mass of the entire observable universe. That would be off by about 50 orders of magnitude. Here, the discrepancy is twice as large. This isn't a rounding error, it's a clear sign that the model is fundamentally missing the point. And the trap runs even deeper. Gravity is the only one among the 4 fundamental forces that pulls exclusively. Negative mass has never been found in nature. Electromagnetism can both attract and repel. It has positive and negative charges. But gravity always pulls inward. It never pushes outward. Trying to build a model of cosmic repulsion using a force that only knows one direction is like forcing a river to flow uphill without a single pump. That's why scientists introduced the concept of dark energy, something fundamentally new that would push outward. Now, let's shift perspective. Not upstream, but sideways. What if we stopped searching for some mysterious substance pushing galaxies apart, and instead looked directly at the edge of the observable universe. The cosmological horizon marks the boundary beyond which light hasn't had time to reach us since the universe began expanding. The holographic principle suggests we treat this boundary just like the event horizon of a black hole, like a screen. A screen that holds information has a temperature known as the Unruh temperature and, as a result, generates entropic pressure, a pressure pushing outward from the inside. We calculate this pressure. Plug in the parameters of the real observed universe. The value we get matches the observed density of dark energy. Not approximately, not off by a factor of 1 followed by 120 zeros like before. It matches exactly. Here's what really seals the deal. The estimates for the universe's expansion rate using the entropy-based model match almost perfectly with those from the standard cosmological model. That very model, which has to introduce an invisible substance filling 68% of everything that exists just to get the same numbers. The entropy approach reaches the same conclusion, but without any mysterious substance. No new entity at all, just a boundary, information encoded there, and the system's thermodynamic drive toward disorder. The same mechanics, a screen, temperature, and an entropic force, explained the inertia of objects, derived the law of gravity, and resolved a discrepancy spanning 120 orders of magnitude. 3 problems, 3 vastly different scales, 1 unified framework. And here, a quiet but persistent thought emerges. If the laws we've long believed form the backbone of reality turn out to be merely statistical echoes of processes happening at the boundary, then what exactly is the space we live inside? Physics has a strange quality. The deeper you dig, the less tangible stuff remains. First, solid objects vanish, revealing the emptiness between atoms. Then atoms themselves fade away, turning out to be clouds of probability. And now, it seems, even the last things we thought were unshakable are slipping away. Space, time, gravity. The holographic principle emerged from an attempt to count the bits of information on a black hole's event horizon. It started as a narrow, specialized problem. But this principle, born from studying black hole entropy, proved to be much more powerful. It fundamentally transformed how we approach the physical laws governing the universe. Thermodynamics, quantum mechanics, and gravity, 3 fields that resisted unification for decades, suddenly began speaking the same language. A language of information encoded on 2-dimensional boundaries, the inertia of matter, Newton's law of gravity, the accelerating expansion of the cosmos. 3 phenomena, each on a vastly different scale, yet behind each lies a single underlying mechanism. The gravity we take for granted, and even Newton's laws, are not the universe's fundamental rules. Instead, they are statistical illusions, born from the thermal chaos unfolding on invisible cosmic screens. Here's the key takeaway this chain of ideas leads us to. Space-time probably isn't a fundamental concept. Beneath it lies a deeper reality, one tied to information and entropy. In other words, what we experience as a 3-dimensional world unfolding in time might actually be a projection, like a 3-dimensional image emerging from a flat film. The film is real, the image just a byproduct. And here, physics falls silent. The question lingers. If reality is a projection, and we are patterns of information on a boundary, what happens to us when we fade away? Quantum mechanics sets one ironclad rule: information can never be destroyed. Under any circumstances, even a black hole swallowing a star preserves every bit of information at its event horizon. Let's say all this is true, that the world really works this way. What changes then, right now, on a regular Tuesday morning over breakfast? Maybe nothing, or maybe just one thing. Every moment lived, every handshake, every conversation cut off mid-sentence, and every one that carried on, every loss, etched forever into the fabric of reality, not metaphorically, physically. Information at the edge of the universe doesn't vanish. It can't vanish. Not a single person you've lost is erased from the world's tapestry. They're recorded forever. We still don't know exactly what this deeper reality behind the projection is. No answer yet. But the question is there, and it no longer belongs only to physicists. It belongs to anyone who, one morning, realizes they live inside something unfathomable, and that this unfathomable something might remember everything.